I will just say this, remember that your goal is to, I look at a molecule and identify, if you're told that it's a nucleophile, identify what the HOMO is, and if you're told that it's an electrophile, identify what the LUMO is. So Nate, come on down and take it away. But don't be offended if I interject, because they pay me to speak in 50-minute increments, and you've only gotten 10 from me so far, so I want you to get your money's worth.
I don't get paid to talk. All right. Okay. So we ended last class period talking again about HOMOs and LUMOs and nucleophiles and electrophiles. And before I begin with anything, I want to really root the importance of what we are going over today. So what we are going to learn about nucleophiles and electrophiles is essentially going to be spoiling the rest of organic chemistry, so both 351 and 352. And so if there is any lecture that you choose to listen to, it should be this one. Because you technically have all of organic chemistry after we learn these few things. The rest of the semester is basically just semantics, with some other details along the way. But so please, if there are any questions, this is, if any lecture, the one I don't want to leave people behind. And so make sure that you're understanding this, help your neighbor understand this, and go home and study this if you haven't been doing that. So as a quick review, so a HOMO is a highest occupied molecular orbital. While a LUMO is a lowest unoccupied molecular orbital. So I believe we used the vocabulary term, we called these frontier orbitals. What these look like is on some molecular orbital diagram, I'm going to make something up here. We've got some orbitals, whatever, we're doing something. Maybe we've got something like we've got sigma orbitals, we've got a pi orbital, we've got a non-bonding p orbital, we've got a pi star, we've got a sigma star, and we got to populate this with some electrons. And this is just an example. I'm not looking at any particular molecule or atom just at the moment. But if I'm looking at this, I can identify my HOMO and my LUMO. So my highest occupied molecular orbital would be right here. Here is my HOMO. And then my lowest unoccupied molecular orbital would be right here. So here is my LUMO. So graphically speaking, that's what I'm looking for, is the highest location of electrons is my HOMO, and then right barely above that, the very next step, the first step with no electrons, is my LUMO. So it will do you well to be able to identify that. Yeah?
When we're looking at these electrons, are these specifically valence electrons?
Yes, it's going to end up that they're valence electrons. And actually, this is a big basis for the importance of valence electrons. In molecular orbital theory, and by the way, the question was, are these the valence electrons we're looking at? So in molecular orbital theory, there's not really so much a concept of bonds as there is just orbital mixing. And all orbitals are going to mix. If we've got something deep in the periodic table, let's look at like iodine bonding with something. Even the 1s orbital in iodine is going to be contributing to the molecular mixing of the diagrams. But we don't care what iodine's 1s orbital is doing. but it is making, there's the 1s sigma, or the 1 sigma, the 1 sigma star, there's the 2 sigma star. All of those are getting filled, populated, but it's the valence electrons where we're finally starting to see the interesting stuff, the HOMO and the LUMO. So only those outermost electrons. Yeah?
If you just had one electron in one of those lines instead of two, would that still be the HOMO?
It would be. Yep, that could still be the HOMO. So if we only have one electron, so an unpaired electron, just a lone electron, is that still the HOMO? Like, yeah, that can still be the HOMO, and we've got a whole chapter on that. It's a radical chemistry. Let's come here.
I was wondering, I know how to identify, obviously, the non-binding or the non-bonding lone pair as the HOMO, but what about the NCP orbital? I know that can be like a LUMO. How do you identify that in like a molecule? Oh, it's got a non-hybridized p orbital.
Good question. So how do we identify if a p orbital is the HOMO, the LUMO, those types of things? We're going to get to that. So give me about probably a couple minutes and a couple other questions, and I will give you a nice memorizable list, if that sounds okay.
If we were to be asked to draw the LUMO in this case, how would you draw a non-bonding p orbital? Or if it was a HOMO with a lone pair, how would you draw that?
Good question. So how do I draw these orbitals? How do I draw what a non-bonding p orbital looks like? How do I draw a sigma star, all that? I will get to that as well, if that's okay. Essentially, that'll be best answered in context. I'm sorry to push that to the side, but we will very thoroughly answer that. Okay. So the first thing that I do want to do is let's just get it out of the way. Let's give you a list of things to look for identifying a HOMO and a LUMO. So when I'm given a molecule, let's look at something like this. Let's look at carbon singly bonded to 3 hydrogens with a positive charge on it. So we're going to look at this. Now, if I see this molecule, it is crucially important to understand what the HOMO is and what the LUMO is if I'm going to predict the chemistry of what it can do. So let's start with that list then. So if I want to identify a HOMO and a LUMO, the first thing I need to know is that every molecule has both a HOMO and a LUMO. So all molecules have a LUMO, or a HOMO and a LUMO. HOMO and LUMO. So with that statement, though, not all HOMOs and LUMOs are created equal. So we could really strain ourselves to find the obscure frontier orbitals of certain molecules, but let's limit that down to simply what's important. So for a HOMO, or rather what we'll call an important HOMO, I am looking for 2 things, and this is a ranked list. So the first thing I want to see is a lone pair of electrons. So if I see a lone pair of electrons, that is going to be my HOMO. Next, if I see a pi orbital, a pi orbital is going to be my HOMO. Now, if I have a molecule, and if I do not see a lone pair anywhere in the molecule, and I do not see a pi orbital or a pi bond anywhere in the molecule, I don't care what my HOMO is. I'll still have one. It's probably going to be some sigma star or some empty orbital somewhere, but it's not going to be significant enough to perform chemistry. So, of course, you could try to find some exception to that, and I know they exist, but they're not profound enough, they're not common enough to where we're going to need to quantify those, especially for the next few chapters. So for right now, that's all you need to look for a HOMO or for a LUMO, is a lone pair of electrons or a pi orbital, again, in that order. Yeah?
Hi. If you have all sigma bonds in a molecule and no pi bonds, would the HOMO be a sigma star or the potential for a pi bond?
Good question. So if I have a molecule that only has sigma orbitals, so like something like methane, let's look at that. So CH4. So H, 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 H. So this guy, methane, has a whole bunch of sigma orbitals. So what is what's the HOMO, what's the LUMO of this? So the HOMO is going to be the highest occupied molecular orbital. The place that the electrons are in these sigma orbitals. So that's where all of the electrons are. And then on the other half, there's going to be 4 empty sigma star orbitals. Now, the question asked as well, is there like a potential for a pi orbital? Is there a potential for a pi bond that is, there for the HOMO or the LUMO? The answer is actually no. So I don't have to think about potentials. I just have to think about what I see. So, yeah.
Can you explain why there is no potential for a pi orbital? Just because the hydrogens don't have a shell.
So yeah, so why is there not a potential for a pi bond? So, okay, so you could certainly do some chemistry that would cause a pi orbital to exist in this molecule. But as far as a HOMO and a LUMO go, I care about I take a picture of my molecule and see what it looks like right now. I don't care about what can happen in terms of what my current HOMO and LUMO is. All I need to know is this is what my molecule looks like right now, and so this must be my HOMO, this must be my LUMO. Now again, you could certainly mix chemicals, do something funky to create a pi bond with something, or a pi orbital with something, but that's not this molecule's HOMO. That would be a different molecule's HOMO and LUMO.
I would do just one other thing there. Hydrogen can't form a pi bond because it doesn't have access to p orbitals. And then the second thing is, what Nate is showing you is if the HOMO of the molecule, which here has to be the sigma bonding orbital, right? There's no other choice. If that's what it is, if it's not a lone pair or a pi bond, chances are that molecule is not a very good nucleophile, and indeed methane isn't. The question about could you do something to the molecule to turn it into a good nucleophile is a good one. And we're going to see examples of that in chapter 2. One, just as a preview, what if you pulled off a hydrogen from this molecule? That's called deprotonation, acid-base chemistry. Use a base to remove a proton off methane. Suddenly the molecule has a negative charge. That actually is going to make those turn what used to be a sigma bond into a lone pair. Now that's a reactive HOMO. So yeah, there are things you can do. But Nate's insight really is really good here, which is if it's not a lone pair or a pi bond, chances are it's not a great nucleophile, so you don't have to worry.
Yeah. Okay, I saw this hand first.
So this is like any molecule, is it always like if you see something like a tetrahedral shape that only has sigma bonds, is it the same pattern? It's always gonna be sigma is the HOMO, is the LUMO. Is the HOMO, and then sigma antibonding is like the LUMO, and then like vice versa, like if it has a pi bond, it's always going to make the pi bond is the HOMO. Is it the same pattern for any molecule?
Yeah, we can, so the question is like if we only have sigma bonds or sigma orbitals, is that going to be the location of my HOMO-LUMO? If I've got a pi orbital in there, is that going to take over the spot? Is that going to be the HOMO-LUMO? The answer actually pretty well is yes. If I have a pi orbital, I'm essentially guaranteed that that is the important HOMO.
Unless there's a lone pair.
Unless there are lone pairs.
So then if it has a lone pair, is that always going to be the HOMO?
Yeah, so if there's a lone pair, then yeah, that is going to be the HOMO. So, and we can work through that. Essentially, what's going to happen is let's imagine a hypothetical molecule. So I'm going to change this guy from carbon to something else. We're just going to call it Y. Y's got a lone pair on it. So this lone pair is now going to end up different in energy. It's going to have its own lone pair sigma location that is going to be higher than a bonded sigma. Now, we don't need to get too deep into this, which is why right now I really want to leave it mostly as just here's a categorizable list of things that we can memorize. Just if we see a lone pair, that's going to be higher in energy than whatever else is going on in the molecule.
And one other thing here, just remember lone pairs are in atomic orbitals. They're lone pairs because they're not involved in bonding. So whereas bonding orbitals like sigma and pi always have a corresponding anti-bonding orbital, the lone pair does not because it's not even in a bond. It's just a non-bonding orbital, and the relative energy of a lone pair, because it's not involved in a bond, is higher in energy than all the other orbitals that are involved in bonds. It's going to be near what we've called our break-even point, or about the energy level of an average atomic orbital.
Yeah. Yeah, so that break-even point is, yeah, that's where that's going to land. And just mathematically, if we're at the break-even point, we're higher than everything below the break-even point. And that's where our lone pairs are going to be. So thanks for cleaning that up. Yeah?
If this is the case where you've got that lone pair electrons, would you not have two in the sigma orbital? Like, would you take two of those away? Just because we don't have another hydrogen anymore?
Yes, yeah. Sorry, I didn't clean up that
No,
that
good.
diagram.
Just wanted to check.
Okay. Yes.
I just wanted to ask why, the reason why there was no sigma antibonding electron in methane, because we know that they're bonded and therefore they can't be.
Yeah, so why are there no electrons in the sigma star of methane, or in this molecule for that matter? So remember back in Chem 105. So it's been a while, but we've got, I always forget if it's the Aufbau principle, the Pauli exclusion principle, it's one of those. So electrons are going to populate the lowest energy orbitals. If there's a lower energy place to live, the electrons will go there. So if I had a situation where, let's even look at this. Let's just erase those electrons here, boot those up to one of the sigma star locations. This is a violation of early principles we've learned in Chem 105. These electrons up here are not happy because there's no reason for them to be there. They can move somewhere else. They can move somewhere lower in energy. So that is why we do not see these electrons natively in the antibonding orbitals, because there's going to be a lower location that they can go to. Yeah?
Is there any circumstance where we get an electron-rich molecule that does end up filling those orbitals? Or?
Do we ever have a situation where we do fill up these sigma star, pi star, things like that? As far as I know, not really.
I mean, it's sort of the origin of the octet rule. If you have more than 8 electrons around the second row atom, you start filling antibonding orbitals.
Yeah. It is the octet rule. Maybe you could find some obscure exception somewhere, but I'm not aware of that, and so you don't need to be either. Yeah?
One thing that I've been a little confused on is how do you know when, like,
Good question. So how do we know if a lone pair is inside of a hybridized orbital or if it's inside of just a normal unhybridized p orbital or something like that? So the answer to that is, once again, going back to Chem 105 and 106. So remember steric groups. So a steric group is a lone pair or another atom. And that's what gives us our geometries, our trigonal planar, our tetrahedral, our bent, our seesaw, those types of shapes. Those are all coming from these steric groups. Because when we have something like this, if we look at this molecule, if I were to draw it with actual correct notation, so we've got a wedge, we've got a dash, we've got two lines. That's because all of these want to be at some optimal angle. So some optical orientation, or some optimal orientation from each other. They want to be as far away from each other as possible. So if I have lone pairs, those do not want to be next to other lone pairs. They want to be as far away from each other as they can be. So if I have two lone pairs, or if I have a lone pair in an orbital, it's going to hybridize, because otherwise it's going to be stuck close to something. If I have an empty orbital, then there's no pressure to hybridize. For example, if I have something like this, I should have used the laser pointer. If I use something like this, this has an empty p orbital because there's no electrons in there, so there's no reason to hybridize. If I tried to become tetrahedral, that would squeeze these hydrogens together. These hydrogens would get closer to each other, and now that's unhappy. That's not good. But by leaving this p orbital unhybridized, because there's no electrons in there, there's no pressure to hybridize, it can stay flat, 120-degree trigonal planar, as far away as they possibly can be. Yeah?
You said that multiple lone pairs will try to stay away from each other. Does that mean that they're also in different phases?
So multiple lone pairs in the same molecule, are those also going to be in different phases? Do you mean like different orbitals, or?
Like with water, are those lone pairs going to be the same phase or just different phases?
So as in like multiple lone pairs they're going to hybridize. Is that?
You said the word phase, and I think you're probably referring to when we draw an orbital and we shade it. Is that right?
Oh, yeah.
And phase has to do with the mathematical sign of the wave function. It doesn't have anything to do with charge. The phenomenon of lone pairs and other groups on a molecule trying to get as far away as possible as the basis of Vesper, and then we use hybridization to explain it. That comes from electron-electron repulsion, which does have to do with charge. So no, it doesn't have anything to do with like the phase of the orbital. It's just that their electron pairs are repelled by each other.
Yeah. Okay. Very good questions. Okay, so that's HOMOs and some other stuff. So again, a HOMO, a highest occupied molecular orbital, is first a lone pair and second a pi orbital. Third, it could be something else, but if it is something else, if it's some sigma star, if it's some, whatever, I don't care what it is. It's not going to be significant enough to help me do chemistry. So now let's talk about important LUMOs. So an important LUMO. So once again, I'm going to give you a ranked list. If I see something that's in spot number 1, that is much more guaranteed to be the LUMO compared to something in spot 2 in the list. So first, what I'm looking for is an empty p orbital. And I will show you what this looks like. Second, I'm going to look for a pi star orbital. And then third, I've got 3 for this one. I'm going to look for a C, and we're going to call this a CX sigma star. So X, we're going to see this a lot in organic chemistry. X is a placeholder often for a halogen or some similar groups. So that's being, chlorine, bromine, iodine, so the far right, so next to the noble gases. That's usually what is in place of X. So if I have a CCl, so a carbon-chlorine bond, a carbon-bromine bond, a carbon-iodine bond, so it's going to be the anti-bonding orbital to that. Now there is a basis for this. What happens when we have a bond to a halogen, especially something like, let's look at iodine. The carbon-iodine bond, so the carbon-iodine bond is super weak. So it's very, very weak. So when I'm looking at its molecular orbital, let me move this stuff out of the way. So carbon, iodine, its sigma splitting is going to be really small. So my sigma star, versus if I compare it to something like a carbon-carbon bond, that's going to be much more profound in its sigma and sigma star splitting. Now for a LUMO, we're looking for the lowest unoccupied molecular orbital. So if I've got both of these in a molecule, if I've got a molecule that has both a carbon-carbon sigma orbital and a carbon-iodine sigma orbital, I'll simply see that if I'm looking for the lowest unoccupied molecular orbital, that's going to be the one closest to the middle, which results in that carbon-halogen bond being the more likely LUMO candidate. And it's a result, again, of that bond being weak. Iodine is so big, it's just a large atom with a large radius. It doesn't care if it's in a bond with something else. Look at iodine. It has 53 electrons. So what? It made one bond, so it effectively gets 54 electrons now. It doesn't really notice that. And so it's a weak bond. From the molecular orbital view, we see it just doesn't split very well. And so that's a great candidate to be a LUMO. Yeah?
So is that always just determined by its mass or its size?
Its size, yeah. That's a very big determining factor. Now, I mentioned at the beginning, and so I guess the question was like, is it just determined by size? Is that what it is? So I mentioned at the beginning of this lecture that I was spoiling the rest of the class. So this question that was just asked is essentially the reason why you need to keep coming to lecture for the rest of the semester, is because we're going to learn all the rules. We're going to learn all the different ways to predict what's going to happen, how I can know when something maybe unexpected might occur, and those types of things. How to predict these exact types of questions. So keep coming to lecture. But mostly, yes, it is mostly just the size.
Why? Can you repeat again? Why? I don't know if you said why the carbon-iodine bond is weak.
So why is the carbon-iodine bond weak? So it's simply because of, again, the size. So if I look at a carbon atom compared to an iodine atom, it is very big size difference, which means that bond is long. As opposed to a carbon-carbon bond, that's going to be very short. So bond is short. So the strength of a bond, this, once again, Chem 105, Coulomb's law. The strength of a bond gets weaker by the distance squared. So as distance increases, my bond gets weaker. So it must needs be that if I have a long bond, a large atom, I must have a weak bond. That is always the case, yeah?
And I think I missed the point you're making with how this affects the LUMO.
So the way this affects the LUMO is that a weak bond means that I don't drop very far. So delta E is small. Where here, delta E is large. So the strength of my bond is determined by how far do I drop. How far does my sigma or my pi orbital go compared to that middle, that break-even point? Yeah?
The amount of energy difference, is that going to affect what the LUMO is, or just how the LUMO reacts?
So let's see, yeah, so like the location of the LUMO, is that going, like how does that determine the chemistry essentially? So it's going to, so the location of the LUMO compared to a HOMO is going to largely affect the behavior of our molecules. The behavior when we mix them in a test tube and see what happens. And we're going to see that right immediately, if that's okay. I have some examples to show.
I think the point is just that if you've already ruled out items 1 and 2 on this list, which Nate hasn't talked about yet, but if you've already ruled out those, then the only thing the LUMO could be would be a sigma star. So which sigma star should be lowest in energy? And the answer is the one that's associated with the weaker bond, because that's what a weak bond means. A weak bond means the sigma bonding orbital is not as low in energy as the other sigma bonding orbitals, and correspondingly that the sigma star for that bond is also not as high in energy as the other sigma star anti-bonding orbitals. So if you can identify a weak bond and there's nothing else going on in the molecule, then that's a good guess for the LUMO.
So let me just clarify. So because the difference in energy is large at the carbon-carbon bond, it's large because it's so stable. But because it's so stable, it takes so much energy to break it, and that's why they're so different.
Yes. Yeah, so kind of that delta E, that big delta E, that change in energy is a result of them being small, close to each other, stable. These are all actually the same thing. If you want to get deep into the thermodynamics, the deep doctrine of chemistry, they're all the same thing. Whether we're talking about stability, whether we're talking about a large drop in energy when we create a bond, doesn't matter how you word it. Oftentimes it's just semantics between, it's the Vesper understanding or the MO understanding or something like that. But they're all synonyms of each other. They mean the same thing.
In one of our problem set problems, there was a pi orbital and a sigma orbital in an acid. So the proton, or the electrons attacked the sigma bond between the proton and the oxygen instead of the pi antibonding in that acid. I was wondering what the rule for the acids or something.
Yeah, so let's start looking at some examples, and hopefully that'll clear that up. So essentially it was part of the problem set question. We've got an acid, we've got a base, and wondering how those are interacting with each other.
I would just say for that problem, you were given enough information so that you could, based on what did happen, you could explain it. I agree, and we need to we'll probably not get to this till next time, but I agree for a carboxylic acid, and if you don't know what that is, that's fine. You've got both a pi star for the carbon-oxygen pi bond as the loop. You would think that's the LUMO, but then the nucleophile goes and attacks the hydrogen. Why is that? And the answer is a little complicated. In some molecules, some empty orbitals are similar in energy. So maybe you've got two options. You can do one or the other because it's not a big difference to do one or the other. We'll learn some things about predicting what happens in that situation. You weren't meant to predict what would happen there. You were meant to explain what did happen. And so that's why I gave you the whole reaction. So that's going to take a little bit more explanation than we got today, I think.
Okay, let's take one more question, then I've got some stuff to show.
Can like go over the rank list real quick? I think I'm a little clueless on what some of the terms mean.
So,
Fuel like carbon, like methane, where they don't have the fuel rules.
so yeah, so what do these mean? Perfect segue into example time, if that's okay. So let's look at examples of these. So I'll give what I can in these next 5 minutes, and then we'll clean up the rest next time we meet. So these are best probably seen through example reactions. So as we're going through these, remember the first commandment, the first great commandment of organic chemistry, a nucleophile attacks an electrophile, or a highest occupied molecular orbital attacks a lowest unoccupied molecular orbital. So, didn't know I could do that. So the first example is, let's look at this right here. So this carbocation. So in this carbon, we've only got 6 electrons. We've done something to this carbon to rip off one of the hydrogens or some group on it. So it's got an empty p orbital. And this is what we're looking for, is we're counting our valence electrons, we only see 6. And so there's 2 electrons missing from that octet. That's where we're going to see an empty p orbital. So now let's combine to this. Let's throw into our test tube some Cl minus. So some chloride. Maybe this was sodium chloride, potassium chloride, I don't care. Some source of chlorine or chloride. So when I see a question like this and I'm asked, predict the chemistry, what I want to do is I want to identify the HOMO and the LUMO of both of these species. So starting with the carbon, my HOMO, let's look at my ranked list. So I'm looking for lone pairs and p orbitals. Do I see any lone pairs in this carbon? No. Do I see any p orbitals? No, I do not. So whatever my HOMO is, I don't care. I don't care what it is.
Pi orbitals.
Pi orbital.
Murmuring is because, but the p orbital is right there.
Yeah, okay, my bad. Yes, pi orbital. Sorry. So yeah, so there's no pi orbital. So there is a HOMO. There is a highest occupied molecular orbital, but whatever it is, it's not on my list of interesting things, so who cares? It's probably some sigma star orbital, or some sigma orbital, but again, it's not going to do chemistry for us. What I do have, though, is an important LUMO. So once again, looking at my list, I'm looking for an empty p, a pi star, or a CX sigma star. So right away, I see number 1 on the list. I see the empty p. The empty p orbital. Now looking at the chloride, once again, I'll look at my HOMO, which my ranked list, I'm looking for first lone pairs. Second, I'm looking for pi orbitals. And I see a lone pair. So I see a lone pair on chlorine. And then my LUMO, I don't really see anything on my ranked list. So what I see is I have one important LUMO and one important HOMO, and that tells me what my chemistry is going to be. My HOMO is going to attack my LUMO. So my lone pair is going to attack my empty p orbital and give me a chemical reaction. So the product of this is going to now create a bond between the carbon and the chlorine. To create something like this.
So I think that's all we got time for today. If you've got your quizzes, just write your name on them and leave them up here, and you'll get credit for participating in the learning exercise. Stay tuned for an email from me later today about how we're going to start next week.